Hello, everyone, and welcome to the third session of our fall 2025 program for the Virtual Inter-University Symposium on Infrastructure Management. For those who are new to VISIM, this is a virtual symposium that is hosted by Professor Pablo Durango-Cohen here at Northwestern University. Today, Nachuan and Chen will be presenting their work on transportation dynamics. Each presentation should be about 20 minutes long, after which we will take questions from the audience. People can speak their questions or send them using the chat feature. I'd like to point out that this meeting is being recorded and will be made available shortly after. And I want to thank you all for attending today. With that being said, we'll move on to our first speaker for this session, who is Nachuan Li. Nachuan is a doctoral candidate here at Northwestern, specializing in transportation systems planning and analysis. His research integrates behavioral science, econometrics, control theory, and artificial intelligence to improve traffic policies and management. Before Northwestern, he earned a bachelor's degree in the Applied Math, Physics, and Engineering program from the University of Wisconsin-Madison. Nachuan, whenever you're ready, you can share your screen and you can begin your presentation.
Okay, so I'm not going to introduce myself again, and today my talk is about congestion in motion, data-driven insights into multi-lane traffic shockwaves. I know a lot of you are not traffic theory people, but if you look at this video, you can see congestion is so ubiquitous on the freeways. This is a helicopter footage of I-90-94 of Chicago. If we look at the road heading to the right side, which is westbound, you can see that the three innermost lanes tend to be much more congested than the outermost lanes. I believe the drivers on these three lanes would be very frustrated when driving in this scenario. And sometimes you can even see that there are vehicles performing aggressive lane changes into the even more congested lanes because they want to head to the O'Hare Airport instead of Wisconsin. So this highlights the need of further traffic analysis to improve our freeway systems. Before I formally start the talk, I would like to share the collaborators of this project. And this presentation would be a tribute to Professor Hani Mamasani, who passed away in July. I would say his guidance has really shaped me as a person, and without his kind support, I wouldn't have made the progress today, and I wouldn't have made these results in this presentation. Okay, so in this talk, I'm trying to answer three research questions. First is how to unpack density in congested traffic, which means I want to understand what causes the different speed when traffic density is even nearly the same. The second question is what are the lateral propagation mechanisms of traffic shockwaves? So, namely, how do traffic congestions spread from one lane to another lane? Third, I would like to see if there is a way to formulate a comprehensive framework that can capture all phenomenon in traffic shockwave propagation. Data is always the most important thing for any traffic flow analysis because it enables us to see the heterogeneous driving behaviors. For this study, we used the TG-SIM dataset, which is collected with helicopters in Chicago and mounted cameras in Washington, D.C. The reason why we choose this dataset is because it has very high time resolution and positional accuracy, enable analysis of both macroscopic and microscopic traffic properties. Furthermore, these two datasets both have a wide range of traffic conditions, containing both congested regimes and traffic flow, and free flow, I'm sorry. Here, we look closely into the two datasets. I-90-94 in Chicago has 6 lanes, which is a massive freeway. So we can see a lot of lane-based traffic behavior. While on the other hand, I-395 in Washington, D.C. has a much longer data collection duration, which means we can see more during the data collection. So they have each of them have their own advantages and disadvantages. To verify this data set works, we plot the vehicle trajectories color-coded by speed for I-90-94. You can see that from lane 10 to lane 12, the traffic tend to be much more congested than lane 13 to 15. And there's also propagation of traffic shockwaves on the left three lanes, most of them being backward. And these graphs verify with the video I showed earlier, where the inner three lanes are much more congested than the outer three lanes. And we can also see a lot of behavior such as lane changes in this data set, which is a good sign. Now finally, let's go to the first study I'm going to present, which is unpacking density. Theoretically, traffic scholars, okay, so first for traffic theory, the three most important quantities are flow, density, and speed. And most scholars in history have formulated these relationships where for each density, there is one single flow value and one single speed value, which sounds like a very simplistic model. And you can see that they all follow similar trend. But in reality, if we look at our own data sets, that's not always the case. For example, for each density value, we see a lot of scattering in speed and flow, which means the existing theoretical models I presented in the last slide do not necessarily lead to a high accuracy in model prediction. To address this problem, we introduced the notion of entropy, which captures the heterogeneity in traffic. The way how we calculate entropy is really simple. First, we divide each space-time window into cells, which are much smaller. And then we count the number of trajectory points in each cell. Finally, we use the Shannon entropy formulation to calculate the entropy value, where a higher entropy value indicates more homogeneity in traffic flow, and low entropy value indicates more heterogeneous driving behavior. I'm sorry. To demonstrate how entropy works, let's see a concrete example here. For both of the position time windows, the densities are 49.5 vehicles per kilometer. However, the speed on the right side is much higher than the left side. If we look at the vehicle trajectories, we also see that on the right side, vehicles tend to follow the same speed with relatively even spacing. While on the left side, vehicles seem to slow down with some of minor lane changes into the lane as well. And the left side, after calculation, has a lower entropy value than the right side. So I know one example is not enough. I'm going to show everything next. So now we do the same thing for every single position time window for the two data sets. And you can see that for each, so the x-axis is density, y-axis is speed. The left side contains all traffic states, and the right side has only congested traffic states. Especially for the congested traffic states, you can see that when the density is the same, a higher speed is correlated with a higher entropy, which means entropy has a power in differentiating the speed values. While if you look at the bottom left, it's not the case for relatively free flow regimes. When density increases, entropy also tends to increase and is not very correlated with speed, which indicates a limitation of the notion of entropy, which is its inability to explain free flow traffic's heterogeneity. Now let's move on to the second part of the study, which is the lateral propagation of traffic shockwaves. So the entropy part aims to differentiate traffic states on the same lane. And this part is a little bit different because it examines the correlation of slowdowns across adjacent lanes. To verify that the lateral propagation of traffic shockwaves exist, let's look at the speed profile for I395 dataset. You can see there are 4 longitudinal locations here. And on the y-axis, it's the 3 links. At time 2,750 seconds on the top, sorry, I don't know how to show the cursor. So it's in the bounding box. You can see that when there is a shockwave on link 5, another shockwave on link 4 seems to occur simultaneously, which kind of indicates some correlation. And this kind of pattern exists at other locations in the dataset. While this pattern is not always true, if you look at the second graph at the same time, while there is a shockwave on link 5, it doesn't necessarily propagate into link 4, and link 4 is in fact in a very uncongested state. This indicates that the lateral propagation of traffic shockwaves may follow a stochastic relationship and needs to be modeled more rigorously. There are 3 research questions I want to answer for the lateral propagation of traffic shockwaves. First is the most important question: do they propagate laterally across lanes? Then, if they do propagate across lanes, what are the mechanisms of lateral propagation? Finally, we would like to understand the causes of the lateral propagation of traffic shockwaves so we can propose more effective traffic control strategies in the future. The 2 key definitions for this part of the study are lateral propagation and recurrence. Lateral propagation refers to traffic shockwaves spreading into the adjacent lane, which is simple. And recurrence refers to a future shockwave occurring at the same time on the same link and the same longitudinal location. So these 2 phenomena are both modeled by our structure, plus their interarrival times are also both stochastic. And here's our general model formulation. The left side is the likelihood of occurrence of a traffic shockwave at time t, given the most recent occurrence time of shockwaves on link I-1, link I, and link I+1, which are the adjacent links and the same link. And this probability is expressed by a mixture, which is shown on the right side. And G is the component distribution, which is for the interarrival time of traffic shockwaves across lanes. Any questions so far?
Question. Do the G's capture in any way? Is there like kind of an intensity, maybe the amplitude of these waves or something like that?
In this version of the model, no. G is that like wave intensity unaware, basically. But in the future versions, I will dig deeper into this structure. Okay, let me continue. Let's see how those notations work in this case. X denotes the range of longitudinal locations. Since we are understanding the lateral propagation of traffic shockwaves, for this stage, I exclude the effect of the longitudinal propagation for simplicity. So we compare the shockwave occurrence at the same range of longitudinal locations across lanes, where t is the occurrence time of traffic shockwave on link I, for example, you can see by the graph, and the most recent occurrence time of traffic shockwaves on the same lane and the 2 adjacent lanes can be seen by the markers on the time axis. Pij is the lateral propagation probability if I is not equal to j, and recurrence probability if I is equal to j. As an example, Pi-1 means how much the component distribution for the interarrival time between shockwaves on link I-1 and link I can explain the entire distribution for shockwave occurrences on link I. And it also indicates the lateral propagation probability, because if it is higher, that means that component distribution can better explain the entire distribution on the left-hand side of the equation. Theta ij is the set of distribution parameters which depends on the function we choose for g. After tons of experiments, we chose the Weibull form distribution because it's capable of seeing the change in risk over time and also the expected recurrence time or lateral propagation time of traffic shock waves. K is the shape parameter indicate the risk of occurrence of shock waves over time. If it is greater than 1, that means a increase in the risk of occurrence in shock waves since the last occurrence of shock wave. If K is equal to 1, then it's very fortunate because this distribution becomes a very familiar exponential distribution, which follows the memoryless property. Finally, lambda ij is the scale parameter indicating the typical occurrence time of the next shock wave. To extract the shock waves from the data set, we identify the slowdowns in the trajectories and apply dB scan clustering to form the shockwave clusters. And finally, we segment them into ranges of longitudinal locations. Here are some results of our model when we use the maximum log likelihood estimation method. This figure shows the component distributions for shockwave interarrival times on I-395. You can see that the recurrence duration of traffic shockwaves across on the same lane seems to be pretty different from pairs of adjacent lanes. And I will explain how they are different by presenting the parameters of the model. The shape parameter K. We see that for the shape parameters on the pairs of adjacent lanes, they tend to be smaller than or equal to 1, meaning that there's a decreasing risk of lateral propagation of traffic shockwaves over time. While on the same lane, we can see that K is greater than 1, meaning that the risk of shockwave occurrence increases over time since the occurrence of the last one. Now the scale parameters. We see that for the same lane, the scale parameters tend to be much higher in magnitude than pairs of adjacent lanes. This is quite intuitive because if you see a shockwave occurring on one lane, in order to form the next one on the same lane at the exact same location, we would need the shockwave to dissipate and then rebuild again, which requires some time. Finally, the lateral propagation probabilities. We can see that on lane 3, P33 is the highest, meaning that the shockwave occurrences on lane 3 follow a recurrence process more likely, while on lane 4 and lane 5, P43 and P54 are the highest, meaning that the shockwaves on these two lanes tend to be propagated from the left side. One major cause of lateral propagation of traffic shockwaves is lane changes. You can see that for cases of discretionary lane changes, if there are more lane changes from the left side, the propagation probabilities also tends to be higher on the left side, meaning that there is a correlation. While this pattern does not necessarily hold for mandatory lane changes, which are guided by the routes, possibly because these lane changing behaviors tend to follow a more aggressive regime, which is not able to be modeled by the shockwave propagation model. To verify that this causal relationship exists, let's see a brief video. A vehicle on lane 5 has executed a lane change into lane 4 after it has experienced a congestion. And at the same time, vehicles upstream on lane 4 slow down to give way to it, which forms a new shockwave on lane 4. More clearly, let's see the raw videos in the data collection. This is from I-395. You can see that the middle lane seems to be quite congested initially, and some impatient vehicles, seeing the speed up of the right lane, have performed lane changes into the right lane. And these maneuvers make congestions on the right lane also occur. So these examples both indicate how lateral shockwave of propagations can be brought by lane changes. Here is the summary of the lateral propagation part. So to answer the three research questions, I conclude that traffic shockwaves do propagate laterally across lanes. And the mechanism of lateral propagations is also quite clear. The interarrival time of traffic shockwaves across lanes approximately follow a Weibull distribution, and shockwaves on the same lane tend to follow a higher interarrival time than pairs of adjacent lanes. Finally, we see a difference in the risk change of shockwave formation on the same lane and adjacent lane. Usually on the adjacent lane, the risk of shockwave occurrence would decrease over time, and on the same lane, it would increase over time. And lane changes, on the other hand, have been identified as one of the major causes for lateral propagation in our study. Now, I'm going to present the last piece of work, which is still in progress. Based on the lateral propagation framework of traffic shockwaves, I would like to formulate a unified shockwave propagation framework, which integrates existing studies and my new study. Here are 7 processes: emergence, absorption, merging, splitting, longitudinal propagation, lateral propagation, and recurrence. So lateral propagation and recurrence have been explained by my previous slides. And emergence, absorption, merging, and splitting are relatively easy phenomena that you can see on the same lane, as shown by the figures here. For a unified framework, we would have to classify those events. For the shockwave processes in the same lane, merging, splitting, emergence, longitudinal propagation, absorption, they are observable because we can identify by looking into the trajectories of the dataset. While what I modeled in the last study, recurrence and lateral propagation, they are latent because we have to infer which of those occur based on looking at the parameters of our model and offer justifications by further looking into the trajectory data. And these processes are all interrelated with each other, which provides a foundation for future modeling. So here are the summaries of my presentation. It's important to remember that traffic flow is non-uniform. So for modern traffic scientists, we probably should not use the one-to-one relationships between flow and density or speed and density for rigorous traffic analysis. Second, traffic shockwaves exhibit very complicated dynamics. There are 7 processes, and the traffic shockwave propagation is very nonlinear. You can see there are splitting, merging, and there's also lateral interactions. The lateral propagation of traffic shockwaves may be impacted by lane changes and speed synchronization, and I hope that this finding could be very conducive for future traffic management strategies. And finally, we would need a unified model to capture the multi-lane traffic congestion evolution. Here are the references. And that's all for my presentation. Thank you for listening, and sorry for being a bit over time.
Thank you, Nachuan. Thank you for a great presentation. And now, if anyone has any questions, feel free to speak up, or you can write them on the chat and I can read them out loud.
I'll ask you a quick question. I mean, first, thank you. I think it was a nice talk. I think that, like, I definitely learned a lot about your work. The question is this: Are there other approaches to model basically the propagation of the lateral propagation of these waves? I think that so your approach, it's a very much an empirical approach where you have like kind of you have essentially assumed a stochastic process that you modeled as a mixture, and then you basically fitted the parameters of the distribution. And so I think it's very
Yes.
insightful. Are there, I'm curious if there's more of like, I don't know, if like a differential equations approach that people have used before.
Um, as far as I know of, unfortunately, for the lateral propagation of traffic shockwaves, no one has rigorously modeled with stochasticity.
I
And
see.
there are deterministic studies carried out by Professor Van Hoifman at Ohio State,
Uh-huh.
and his work did provide some insights, but it's rather theoretical without like referring to the data sets. And he mostly studied speed synchronization
Mhm.
rather than shockwave propagation that are caused by lane changes.
Thank you, Nachuan.
And Jürgen, I don't know how to
Oh,
pronounce your name.
Jürgen, that's great. Thanks for this very nice presentation. I have two questions. One is more for clarification for the first part, and then other one might be more outlook. So the first question would be, if I understand correctly, for your entropy measure, you discretized the space and counted how many points appeared. If this is correct, how do you choose the window size, and how would the result change, and what would be the optimal window size? And the second question is for the lateral wave, shock wave propagation. How can we avoid this? What would be then tools or things we could implement to avoid this kind of emerging behavior based on your work?
Thank you for your questions. So to answer your first question about the window size selection of the entropy model, it's indeed very tricky. And we submitted this paper to TRB, and we did get a lot of feedbacks about this. So you're not the only one. So it's a very good question. What we did in our most recent work is to test different window size cell sizes, and we picked the one that has the best scattering. Or in other words, we also build a entropy aware traffic model, which is which are some mathematics I didn't present in this presentation due to time constraints, but those models make flow as a function of both density and entropy. And we would find the, how to say that, we would find the window sizes for entropy that yields the highest likelihood of our model. Does that answer your first question? Yeah. I don't
Yes,
quite
it did.
remember
Yeah.
the exact window size, but I can look
No,
into
it's
that.
fine. Yeah.
It might be sensitive depending on the data set, so we have to be careful on this. And the second one is, well, you asked me about can you repeat the second question again?
The second would be more like, I guess, outlooking. So what would be the practical
Okay, I see.
implications
Yeah,
of your
now I
model, and
remember.
how can this be used to enhance the current situation?
Okay. I can think of two approaches. The first approach is by leveraging automated driving behavior. We like if there happen to be some automated vehicles in the system, I hope at some point in the future the penetration rate of automated vehicles will be relatively high. We can program those automated vehicle trajectories to dampen those shockwaves as predicted by our model. That's one strategy. And the second strategy would be using transportation economics. It would be relatively hard. If there are sensors on the vehicles or cameras on the freeway, we might be able to identify shockwave propagating lane change or speed synchronization maneuvers and we send a warning to those drivers or even levy sort of like behavior-based tolls to discourage these behaviors.
Thank you.
Thank you.
Thank you, Pablo and Jürgen, for your questions. Are there any other questions from Nachuan today? If not, thank you once again, Nachuan, for an amazing presentation. And now we can move on to the second part of today's session. I'm going to introduce our next speaker, who is Chen Zhang. She is a PhD student at Princeton, who is advised by Professor Jürgen Hackel. Her research focuses on developing advanced network-based methods for studying complex infrastructure systems with an emphasis on higher-order network models for mobility, resilience, and transportation analysis. Prior to Princeton, Chen earned a master's in artificial intelligence engineering from Carnegie Mellon. Chen, feel free to share your screen and you can begin your presentation.
Okay, hi everyone. My name is Chen, and I am a second-year PhD student from Complex Infrastructure System group at Princeton University, and I'm working with Professor Gehackel. Today, I'm excited to introduce my work about capturing human mobility dynamics in transportation networks using a higher order network perspective. Can you hear me clearly? I'm not sure.
Yes, perfect.
Yeah, okay, got it. So let's start by thinking about question. What makes transportation systems special? If you model transportation network as a network, they are physical networks, mostly planar, where we can compute all pairs shortest path with upper-bounded computational complexity. But for me, the reason makes it super complex is the people using them. Transportation networks aren't just about connectivity, they are shaped by how people move through them. Every day when we are trying to drive, we make tons of micro decisions, which lanes to take, whether to turn, how to react with the traffic, and all the things based on our experience, our habits, and the context, as well as the infrastructures. These individual decisions leave traces on the data, and they somehow cannot be fully captured by the aggregated flow counts. And naturally, these human behaviors embed context into the movement data, creating what we call memory effects here, or sequential dependencies, which needs to be accounted in a realistic model. However, a standard network representation often assumes decisions are memoryless and transitions are independent. That's where things start to break down. Okay, let's went back and have a brief overview about a standard network representation. It models road systems as a graph combined of sets of nodes represents for road intersections and sets of edges represents for road segments. Which means in this setting, if you have an edge from A to B, you have an edge from B to C, you are supposed to have a path from A to B to C. That's transitivity. However, in the real world, transportation networks, it may not always hold true. Imagine the first scenario, you are driving on a ramp or a diverging lane. On paper, the road from A to B and B to C exists. But because of things like solid lane marking guardrails or the ramp curvature, you actually cannot go directly from A to B to C. So here, the transitivity is blocked by the geometry of the road. And another case is like, imagine you need to make a left turn in this road. Before this, if you are not in the correct lane, you need to change your lane earlier. But if the traffic is too dense, you cannot move over. So in this case, transitivity is violated by the dynamic traffic conditions, by what we say like how drivers behave here. So just chaining links together doesn't always give us a valid path. We need models that account for how people arrive at a node instead of just where they're heading next. So here we are trying to overcome this and introduce our higher order networks. Instead of representing the movements as independent hops, we encode path segments like path from A to B to C as our nodes. The key idea here is where you are coming from should give you some information about where you are heading to. The mathematics underlying is pretty straightforward. It's a higher order Markov chain, which means instead of taking only the current states, we take care of the previous k states, which means like a k-length memory. And then we give the transition probability based on how a specific k+1 exact transition occurs in all those continuations from the same prefix. For example, given you are coming from A to B, was how many times it goes from A to B to C, and how many times it goes from A to B to D, things like this. And by leveraging this, we capture the memory inherent in path data. So how we form a higher order network? Think about this. You have for agents traverse on the graph, you got all the path from those agents. You extract the subpath length of 2, and then you figure out the connectivity of all these subpaths. Thanks to the work done by Ingalls group, we can represent these higher order relationships using called a debriefing graph. In this framework, each node becomes a k-tuples of consecutive road intersections. For k equals 2, a node might be an edge like A to B, and for k equals 3, the nodes can be a path from A to B to C, and so on. In this way, the edges link overlapping like k-tuples, preserving the sequence. And naturally, we can attribute the weight of the higher order edges by the higher order transition probabilities. Like here, for example, we can give the weight of A to C to C to E based on the probability given A to C, we go to E. And as a result of like we're keeping a network representation, we can apply all those kinds of classical network analysis tool, like between the centrality, PageRank, and so on, to this higher order network. Like the between the centrality is a shortest path based centrality, like you calculate all pairs shortest path, you quantify for each node how many times this node occurs in all these shortest paths. And in this way, it was commonly used in transportation networks as a approximation of the traffic flow. And PageRank is a random walk-based one. Like if you are a random walker traverse on the network, how many times you stay on this specific nodes. And also the path prediction based on the inference of the higher order Markov chains. In this way, the higher order network representation embedded the memory effects allows us to move beyond the shortest path and the random walks. And the workflow here is pretty straightforward. We get the path from simulations via agent-based model like VISIM. We got the path from the real world, and then we extract all the subpaths of length k. We treat each subpath as a kth order nodes, and then we link subpaths that overlap by k-1. In this way, we have the structure or topology of the higher order networks. And if you want, you can attribute the higher order transition probability we described previously as your edge weight and form a stochastic higher order network. In this way, we can do the structural analysis like the between the centrality and the importance ranking and the functional flow prediction on this higher order network. We apply this higher order network framework to 2 kinds of networks. The first one is the path simulated via VISIM on the surface serial network, and also the real world trajectories on city scale networks in China, Shenzhen and Jinan. If you compare the between centrality and PageRank with the real world road usage, you will find like it gives better alignment with the actual simulated traffic flow than with the first order network. And also more importantly, is like at order 3, beyond which the model starts overfitting, it gives us a sweet spot. And a very brief description here. When we're comparing the between centrality and the ground truth, we use the KR divergence, which is the smaller, the better. And when we're comparing the page rank with the actual usage, we use the Kandel-Tau rank correlation, which is the higher, the better. And if you take a closer look at the distribution of the between centralities and the ground truths like road usage, you will see the higher order shows better alignment, but decrease with like more than fourth order, which means that we define a sweet spot. We don't need to use all the history or the infinite history to capture the short-term behaviors here. And also we do the path prediction based on the higher order transition probabilities. We found that even with one more step, it has a boost of predict accuracy for the next step prediction about 23%. And also the rising cross entropy at fourth order indicates a overfitting, which is related or corresponding to the previous findings. And we also compare our next step prediction accuracy between the higher order, between the inference on the higher order networks and the sequential models, sequence deep learning models like LSTM, GRU, transformer things, and GNNs. We found what's interesting here is like the higher order networks performed on par with these deep learning models with their simpler and interpretable structure. And this provides that behavior evidence that people's next move depends heavily on just a few past steps. But if we take a look at the data amount or the data set size we use to train this, the sequence deep learning models definitely takes more data to learn this pattern, as they don't have the network topology constraint handling. And as far as that, the higher order network relies on the several, like that amount of the path, because they use the probabilistic path structure learned directly from the observed transitions, and it's with the network topology constraints. This makes these high order network as a great predictor, which can be valuable for the real world settings where data can be sparse, noisy, and privacy restricted. And we extend the similar framework to city-scale transportation networks in Shenzhen and Jinan. It shows really similar behaviors. Like the high order, the third order page rank shows the best alignment with the ground truth, with the real world road usage, and the path prediction has a large improvement for a higher order Markov chain use. If the numbers are not enough to describe the improvement that higher order networks gain, we can take a closer look at the real world case study. In this 3D visualization, we visualize the real world usage on Jinan Road network. Here, the height represents how frequently the road intersection is used. And the orange circled area is somehow the busiest area. But we can take a closer look at this specific area, and we find that this certain area are especially busy, maybe likely due to the nearby parks, the schools, and the colleges, many things. But if we overlay the page rank on our city map, we will see that the first order page rank totally missed this critical area, and it emphasized more on the areas more on the center of the network. However, if we take a look at the higher order models, they pick up on them and show a closer match with the observed flows and highlighting the actual usage of the road infrastructure. And this demonstrates that the higher order matrix better captures structurally important area tied to the real human movements, things like the important major transit hubs or things like that, which a memoryless model would not state fairly. And for the conclusion and future work, To summarize, we developed a higher order framework that capture memory effects on the transportation systems. We validate the path prediction accuracy improvement in both benchmark and city-scale networks. We showed that higher order centralities better reflect actual traffic patterns, and we identify a sweet spot order that balances accuracy and feasibility. At the same time, it can also be a game changer for the transportation planning and infrastructure optimization applications. Thank you so much for my advisor, Jürgen Hackels. Thank you so much for the organizers of VISIM. And thank you all for attending. I'm happy to take any questions.
Thank you, Chen.
Thank you.
Are there any
And-
questions from the audience?
Again, thank you for the nice talk, Chen. I think that it was quite interesting. So just a quick question. Basically, when you increase the order, essentially, like kind of to account for the memory, essentially, what is the runtime of the what is the runtime of the I don't know, I guess essentially estimating the probabilities because basically, of course, the state space, it's increasing essentially exponentially. And so the reason why I'm asking this question is because I think that it would seem that there would be a lot of opportunities to improve the computation of these probabilities, maybe rather than like kind of imposing the same order across all trajectories, like kind of doing this by sampling and by focusing on some specific trajectories, which also might be insightful into the way people make decisions or the conditions of the network that basically might lead to the need to capture this history in anticipating what the next move is going to be. Sorry for the long-winded question.
No. Yeah, it's the first, if I'm understanding correct, the first thing is like how we'll expand the higher order networks if we increase the order. Currently, because we are building up the higher order networks based on the path. So the dimension of the networks increase linearly. But if you are taking all the topology, all the possible higher order states into account, yes, it will increase like exponentially. But the transportation network is a very special context. We got the physical network. We got the path like is feasible in the network, and we have the information about the OD pairs or things. So it limits the possible states of the higher order networks. And the second thing is, I think yes, we can definitely improve this higher order networks, and I think this also relate to how to build a good network representation for the networks. For example, if you have an edge, if you have a node have only degrees of 2, which means like you have only like one legal next state, you definitely goes that way. You don't need to like try to capture this transition probability in your higher order networks. That's also our next step for normalization of the row networks and the higher order representation for the row networks to give the most concise, most useful network representation for capturing the essential dynamic behaviors on the network. Yeah, thank you.
Are there any other questions for Chen? If not, to conclude today's session, I want to thank Chen once again for an amazing presentation. Thank you also, Nachuan, for participating today, and thank you all for being here. As a reminder, we are already looking for speakers for the 2026 spring edition of VISIM. So if any of you know of any students who may want to participate, feel free to redirect them to our website and they can sign up. Other than that, thank you all once again for being here, and this concludes our session.